Greetings to you. We will start off where we left in the last class. I think I had shown you this slide where the electronic excited energy levels involve large amounts of energy from 35 to 35.7 kilocalories in the visible range to several hundreds in the far ultraviolet range. Each electronic level, we have to understand that it is associated with several vibrational modes. That means, other energy levels which are associated with, which are in smaller size, but maximum population is always at vibrational level 0. Consequently, the absorption arising out of this transition will be maximum. So, it will be most intense. So, this tendency is normally enhanced in the liquid state, where the vibrations are further dampened by intermolecular interactions. Usually what happens is a broad absorption band results. Suppose we take the electronic spectra from a vapor state. In that case what happens? The electronic transitions will become much more sharper compared to liquid state. And compared to liquid state, solid state electronic transitions, if you take the spectra, they will be still broader, the interactions will be weaker. So, coming back to this transitions, we say sigma to sigma star transitions are very energetic. That means, transition of electrons from single bond to excited single bond structure. So, such energetic things, energetic transitions are found only below 200 nanometers, that is in the vacuum ultraviolet region. Consequently, compounds or elements which have absorption bands below 200 are very difficult to measure in ultraviolet or AAS, atomic absorption spectrometry. Also, compounds in which all the electronic valence electrons, all the valence electrons are most intense. Now, let us look at atoms in the Hindu scriptures. This I had also mentioned in the last class, that we call them Anu, Paramanu and Kana. Kana is an aggregate of smaller particles, Anu called as Anu, but it is not visible to the naked eye. Anu of each substances are distinctive and capable of independent existence. Paramanu is the smallest discrete particle capable of independent existence, but not visible to the naked eye. So, Paramanus are essential components of all the things we see around us. The power of the Paramanu and Anu was utilized in the warfare even in Puranas, which are known as astras. In modern day terms, you can call them warheads, and then these astras in Puranas are described as Shaktastra, Brahmastra, etc. And in aeroplanes also they used to carry these things, they used to be known as Vimanas. But coming back to the modern times, we have Dalton's theory, which was propounded in 1802. So, what he said is matter is composed of tiny real particles called as atoms, which are kanas or paramanus or anus, whichever way you feel describing corresponding equivalents, which are these atoms are indivisible. This was in 1802 by Dalton, and he said they cannot be created nor destroyed. That means, every atom in every element is capable of independent existence. You cannot cut it down further into smaller particles, which we know is not true nowadays. So, but what he said at that time must have been relevant, and what he also said is atoms of all substances are identical in nature. This is also in consonance with Indian philosophy, that every human being individually is alike, and except maybe finer details, but they are made of the same 5 elements, that is Panchabhutas, Akasha, Vayu, neeru, water, and then fire and sound. These are Panchabhutas. So, atoms of pure substances and others differ in weight and other substances. So, if there are more more atoms in the in a particular element, it looks different. If there are less atoms, it looks different, but each of them are having separate characteristics owing to the number of atoms present in a element, in an element. So, we also said atoms combine in definite proportions resulting in chemical compounds. So, that is also a very important concept. That means all compounds are having number of elements, but mixed in definite proportions. For example, if we take water, it will be having hydrogen and oxygen mixed in 1:2 proportion. One is 1 of hydrogen and 2 of oxygen. Atomic weight will be 2 of hydrogen and 1 of oxygen. So, down the line, many of these atoms were also found to be divisible, but Dalton's theory can be again extended to number of divisible components. For example, now we know that an atom contains an electron. Now we can extend Dalton's theory that electrons are not divisible, but subsequently we also know that electrons can be divisible and they may or may not have independent existence, but right now what I am showing you is a fundamental list of components called as elementary particles. They may or may not have independent existence, but the particles which I am showing you in this slide are the ones which we recognize from our scientific vocabulary, atomic vocabulary, and these include electron, it is denoted by E, and mass is in atomic mass units, it weighs approximately 0.0005486 and its charge is minus 4.8029 ESUs into 10⁻⁻10, and relative charge is that is what we use in day to day application is we denote it by minus E, because electron carries a negative charge. Corresponding proton which carries a positive electric charge, its mass is approximately 1.00757. So, its charge is exactly same as an electron and denoted by P. Then we have what is known as neutron. This is also Dalton's according to the Dalton's theory and modern atomic theory, denoted by N. Weight is approximately equivalent to a proton 1.008 and charge is neutral and relative charge is also neutral. Then we know what is known as positron. There is no symbol as such, but it is exactly same as an electron, and but it has positive charge compared to electron. Electron carries negative charge, whereas a positron will carry positive charge. This does not have independent existence. Similarly, we have other particles known as neutrinos, which does not have any mass, but charge is also 0 and relative charge is also 0. Then we have what is known as antineutrinos, again no charge. Mesons are there which could be positive or negative charge, and it can be denoted by plus or minus E. Similarly, mu mesons, positive or negative. Deuterons, deuteron is nothing but 2 hydrogen atoms. So, the mass should be 2. If we take hydrogen as 1 or proton as 1, proton and hydrogen are essentially same. So, deuteron is 2 hydrogen atoms fused into one. So, the mass charge will be same, because it contains 1 proton and 1 neutron. So, positive electron. Similarly, alpha particles, that is helium atom having 2 positive charge. So, these are the basic fundamental particles of atomic mass as modified by the Dalton's theory. Dalton's theory has been modified to include all these fundamental patterns. So, now we can summarize modern atomic theory as an atom consists of a positive charge and nucleus, that is nucleus, and comparatively heavy, because proton is heavier than electron, and then it has an extranuclear arrangement of electrons which is comparatively large and diffuse in character. That means, electrons are hanging around a space, a circular space, spherical space around the nucleus. So, nucleus consists of number of protons and neutrons, and they are formally related. So, protons are related to neutrons as proton gets converted to neutron and a charge, and this mesons, pi mesons can be converted into mu mesons plus some frequency discharge, radiation discharge, and the mesons also can be converted into different particles, fundamental particles, and all these things can happen during radioactive decay processes, not in normal circumstances. So, changes in nuclear charges occur according to the following mechanisms. So, now we tell that the basic element atom consists of protons, neutrons, pi, mesons, this, that, etc. But for all practical purposes, if I want to describe a stable electronic structure, I should imagine a nucleus with neutrons and protons with electrons around it in the spherical space. Now, when an element becomes stable, there is a rule of 8, and nuclei, now I am talking about nuclei, not the electrons. Nuclei with 2, 8, 20, 28, 50, 82 or 126 neutrons or protons are especially stable. That means, any element having 20 atomic mass is stable. It may consist of neutrons or protons. It may be having 50 or 82 or 126. These are called as magic numbers. They represent closed shells of nucleons. For a given element Z with Z protons, a number of species may exist with the same number of protons, but varying in the number of neutrons. What we are saying is the protons in a given, for a given element, it has to contain, its nucleus should contain neutrons and protons. So, protons and neutrons with 2, 8, 20, 28 etc., they are all stable, right. So, the stable elements may have different combinations of protons and neutrons, but still correspond to 50, 82, 126 or 2, 8, 20 like that. So, such elements exhibit the same chemical properties, but differ in atomic weight. So, these are called as isotopes. So, what are isotopes? Isotopes are substances which carry the same number of protons, but varying number of neutrons. So, neutrons do not carry any charge. So, so long as the element remains the same, neutrons may vary a little bit, 1 or 2 extra this side that side, but then they are they exhibit same chemical properties. So, these properties and elements having such nuclear structure are called as isotopes. It may also happen that nuclei with the same mass number, but differing in charge. That means, we are talking about different elements, but weight is same. So, these things have exhibit atomic different chemical properties because they are different elements, but their weight is same. So, such elements are called as isobars, but they do differ in their properties. For example, calcium and argon, they have different atomic number, different number of protons, but their total atomic weight is almost same. Okay. So, how do these neutrons and protons normally exist? Because protons carry high positive charge, neutrons do not carry any positive charge. So, how do they hold each other is a question. So, normally what we say is attractive force exists between neutrons and protons. They are very weak forces. So, by weak forces they are all held together. So, energy exchanges occur between protons and neutrons via mesons among them. So, the actual neutron to proton ratio is due to the balance between the tendency towards neutron proton equalization and proton reduction. So, all the radioactive decay processes are therefore aimed at obtaining stable nuclei. So, if you look at some of the electronic structures of radioactive elements, they keep on radiating alpha radiations, beta radiations, gamma radiations and all those things. By emitting the radiations, their mass and charge will keep on changing, but decreasing also. So, when they keep on decreasing, they move towards a periodic table where the atomic weight and atomic number keeps on reducing, and we know many elements in the periodic table which are having very low atomic weights and atomic numbers. And most of the elements what we see, iron, cobalt, nickel and all those things, including calcium, magnesium, etc., lead, all these things end up having lower atomic weight, so that they do not become radioactive materials. So, any radioactive material which is having a higher number of neutrons and protons in the nucleus undergoes radiation to give you a stable, but a stable element which is having lower atomic number. So, that is where most of the radioactive decay processes proceed. So, the actual neutron to proton ratio is due to the balance between the tendency towards neutron proton equalization and proton reduction. So, this can be achieved by beta emission. This I have already explained to you. Neutron proton ratio will change, neutron emission also will reduce the atomic weight, positron emission will not reduce the atomic weight, orbital electronic capture quite possible, but and proton emission definitely will lead to lower nuclear weight or lower atomic weight. So, an unstable nucleus arising out of radioactive decay or nuclear attraction readjusts itself to a stable nucleus by the emission of a particle. If the process mass is lost by alpha particle, if an alpha particle is lost, the mass loss will be 4 atomic units and charge loss will be 2 units. Okay. So, because an alpha particle corresponds to a helium atom. So, it keeps on losing alpha particles from the nucleus until it reaches a stable configuration, that of, for example, that of lead. So, nuclear stability is also attained by the absorption or release of energy. So, the energetics of nuclear reactions are of course associated with mass changes according to Einstein's equation, which is a very famous equation. I have written it here, which says that E is equal to mc square. That means the amount of energy released is a multiple of its mass and velocity of light squared. Okay. So, the release of energy takes place either in the form of heat or radiations. If it is heat, it will be enormous like in an atom bomb, and if it is radiation, you can still feel the heat, because most of the neutrons, when they pass through actual materials, they generate heat, but not as much as in a nuclear bomb. So, the mass change corresponding to different conversion of hydrogen into helium. For example, if we take a look, I want to convert hydrogen into helium. So, hydrogen is having 1 proton, helium is having 2 protons. That means, I have to take 2 hydrogen atoms or 1 hydrogen and 1 neutron, and then convert it into some sort of a combination elements with the amount of heat released to convert the essential difference in the mass between hydrogen and helium. So, if I write that equation, you can see here on the slide that I have written here 2 hydrogen atoms of 1 mass each plus 2 neutrons of 1 mass and no charge will give rise to 1, 2, 2 and 2 is 4 atomic mass, and it gives you 2 atomic number plus some amount of heat Q, and the difference is 0.0302 atomic mass units. The energy difference Q corresponds to this much. That means, so much of energy is to be released when we form a helium atom starting from 2 hydrogen atoms and 2 neutrons. This is equivalent to 28.12 mega electronic volts of energy per helium atom, or 6.45 into 10 raised to 8 kilocalories per gram atom of helium. I just convert per atom into grams. So, this is equivalent to the temperature prevalent in the sun, on the sun. So, 6.45 into 10 raised to 8 kilocalories is the amount of energy that corresponds to the mass change when a helium is formed, and this kind of energy corresponds to the temperature prevailing in the sun. Therefore, we assume that the sun is having almost all the elements that are present on the earth, but they are being formed and being destroyed in the atmosphere of the sun, in sun's atmosphere. So, nuclear reactions are of interest to us as a source of energy, because if I can combine 2 hydrogens and 2 nitrogens and form helium, I should be able to generate so much amount of heat. I can do lot of things with the amount of heat that is generated by such a reaction. So, there are 5 types of nuclear reactions. One is capture reaction. I can capture the electrons and protons and neutrons. I can have particle-particle interactions, and then I can have fission reactions. A big element can be converted into smaller elements, and then spallation reactions, and then fusion reactions. I can take 2 elements and fuse them together. So, another way of classification for these things are in terms of bombarding agent. I can take alpha particles to bombard and carry out chemical reactions. Proton induced reactions, I can take protons, deuteron induced, gamma and X radiation induced, and neutron induced reactions. All these are such reactions can be carried out in atomic reactors with adequate precautions. They cannot be carried out in normal laboratories prevailing in the sun. Now, that is about the nucleus. You remember that we have been discussing the atomic structure basically because we have to know how an atom looks, how an atom works, how an atom can be utilized in the chemical analysis. So, now we know that there are atoms, all elements are made up of atoms, and the atom consists of a nuclear part as well as an electronic part. So far we have discussed about the nuclear part. Now we will discuss about the electronic part. So I have said that electrons are there in the spherical atmosphere around the nucleus. Now how do we know that the spherical structure contains electrons? They must have been found by somebody, they must have been detected and determined by somebody, and it was Sir J. Thomson in 1904 who proposed the corpuscular theory of matter. He pictured the positive charge of an atom distributed uniformly throughout a sphere of protons and neutrons of about 10 raised to minus 8 centimeter. Okay, that is 1 angstroms. So negative charge was surrounding it in a jelly like fashion. That is his imagination. So Rutherford modified this theory that electrons revolve around the nucleus in such a way that the centrifugal force, electrons are revolving, and the centrifugal force generated by the electrons is exactly balancing the inward attractive forces of the electrons, just like our planet go around the sun. Now there is a vast similarity between sun and planets and nucleus and electrons. So the electrons are going around the nucleus round and round and round, and the electrons are attracted towards the proton, but they do not fall into the proton. That means it generates centripetal force, centripetal and centrifugal forces, that of attraction and repulsion are exactly matched in a stable nucleus. So this view was also not tenable, because if they do not match, the electrons will fall into the nucleus, generating nuclear reactions. So regardless of their speed, they enter the nucleus some time or the other. Moreover, the electron losing energy would emit continuous radiation. Now imagine an electron is going round and round, okay. It's attracting, the nucleus is attracting, it is very heavy, 1840 times heavier than the electron. So it keeps on attracting, and sometime it falls. But if it is falling into the nucleus, it would be slowly losing its energy, its own energy, and it must be emitting radiation. This does not happen. That means the electrons around the nucleus are moving around in such a way that they do not fall into the nucleus. That is the catch. So Bohr proposed a radically different view of the atomic structure based on the optical spectrum of hydrogen. He included that two postulates of quantum theory proposed by Max Planck. What did Max Planck say? And Bohr proposed that the electron in a hydrogen atom always moved in a fixed circular path. That means it will never fall into the nucleus. It describes a circular path around the nucleus. Such a circular path is named as stationary phase state, where the electron is moving around. The angular momentum of each stationary state was an integral multiple of nh by 2 pi. N is number of electrons, h is Planck's constant, pi is you know what it is, 3.142. So this describes n is the number of stationary state. So, this amounts to angular momentum. This angular momentum is given by mvr is equal to nh by 2 pi, where n is called as a quantum number. He also postulated that as long as the electron remains in a given orbit, it neither radiates energy nor absorbs energy. So, when the electron moves from one orbit to another, it was considered to involve the absorption or emission of a definite quantity of energy corresponding to the difference between these stationary energy levels. So, this energy manifests whenever electron moves from one energy level to another energy level, the energy is dissipated, and the frequency it is dissipated as radiation, and also because the energy is fixed, the frequency of such radiation manifests as a spectral line, which could be related to the energies of electron in the two states, that is previous higher energy state and lower energy state, that I designate as E1 and E2, and the difference between E2 minus E1 is the energy difference that is radiated as heat or a spectral line. So, when the elements are when the electrons are moving one state to another, it may fall from fifth energy level to first energy level, or it may fall from third to second energy level, fifth to fourth, fourth to third, all of them 1 5 4 2 3 4 can all fall into 1, 3 4 5 can fall into energy level 2, 4 5 6 can fall into energy level 3. So, the energy levels corresponding to each state is different. So, a single element containing a single electron can generate number of spectral lines when the stationary energy level are involved and transition occurs. So, a single hydrogen atom can give rise to number of energy and states, and they can be detected spectrally, because the energy difference corresponds to the wavelength, and that can be related to frequency. So, all these things can be shown as different lines in the spectra. So, the line spectra of hydrogen contains Lyman series, a number of spectral lines corresponding to energy electrons moving from 2, 3, 4 etcetera to 1, and then this is in ultraviolet range, vacuum ultraviolet, and then it is a Balmer series, another series where the electrons will fall from 3, 4, 5 etcetera to n is equal to 2, that is second electronic level. Similarly, we have Paschen, this is in visible range, Balmer series. Paschen series is where 4, 5, 6 will fall to 3, bracket series will fall to 1, and Fund series will fall to n is equal to 5. So, the Bohr's theory could explain the spectra of hydrogen, but it failed completely when it was applied to multiple electronic systems. Further, it could not account for splitting of optical lines when spectroscopes of high resolving power. Sometimes you will see 2 frequency lines. So, Bohr's theory could not explain. So, this is the picture of an electronic transition, where the Lyman, these are the Lyman series, where all the electrons are falling into the state 1. This is Balmer series, this is Paschen series, and this is bracket series, and this is Fund series. So, a single hydrogen atom can give rise to number of spectral lines.